Hey everyone, welcome to this live session of your daily equation. I always look forward to these Friday sessions, I have to tell you. It's my favorite thing to interact live, spontaneous, as opposed to the things that we film to try to get some of these ideas out there. Obviously, the quality of the live is not quite as sharp as the quality that we can get by doing filming just before we send them out. But the live really has an energy that I certainly enjoy. So anyway, let's begin. And I hope you don't get tired of this, but I always love to see it. If you could just sort of chime in and let me know where you're watching from. I see someone is there from Italy, someone from Staten Island, and a variety of other places scroll by, which is fun. And then please feel free to send in Germany as well. Send in any Turkey and London and so forth. Send in any questions that you have, as I would love to get to as many of them as I can. All right, so let me begin with, as the countries and cities scroll by, let me begin with a question that we have from YouTube, and then I'll go to the live chat that is scrolling by as I'm talking to you right now. So let's see. Andrew, coming from YouTube, asks, Professor Greene, if you see this, I was wondering if the different interpretations of quantum physics agree that a particle doesn't have a well-defined position before it is measured. And the answer to your question, Andrew, some people may find a little bit surprising, because we're so used to quantum mechanics telling us that this world is this nebulous collection of probabilities until an observation or an interaction forces the world in some sense to choose one definite outcome from the range of possible outcomes allowed by the quantum laws. And that suggests, and indeed most physicists do have the perspective, that a particle does not have a position until it is measured. That is the standard interpretation of what quantum mechanics is telling us. But there is an approach to quantum mechanics that doesn't get a whole lot of attention. It was developed by Prince Louis de Broglie back in the 1920s, and also by David Bohm, a physicist who kind of rediscovered this idea. I think it was in the 1950s. And in that approach to quantum mechanics, which makes the same predictions as standard quantum mechanics, it just has a different, slightly different mathematical formalism. There's an additional equation beyond Schrodinger's equation. And maybe I should do that in one of these Your Daily Equation episodes, just to show that equation. But in this approach, particles actually do have definite positions before they are measured. There is no measurement problem in the de Broglie-Bohm approach to quantum mechanics. There are other weirdnesses to this approach. There's the capacity right in the equations to do something over here and to immediately influence something over there, not just through quantum entanglement, which is weird enough, and that's in standard quantum mechanics. This is a more in-your-face non-locality. Doing something here affects something over there. And I think that's why many people don't take the approach as seriously as they might. But to answer your question, Andrew, yeah, there is a different interpretation of quantum mechanics in which particles do have definite positions. So that is not a universal quality of all approaches to quantum mechanics. All right, let's see what we have here. Don Francisco asks, how is it that time can be different for people in space compared to Earth? I have never understood this. And Don, yeah, you wouldn't understand that if you didn't study, say, the general theory of relativity. If you base your understanding of the world, as most of us do, except the weird group of physicists who sort of spend their lives investigating the universe in the language of mathematics, that shows us that observations can be misleading. But if most of us base our understanding of the world from experience, from observations, then yeah, we would come to the conclusion that time elapse is the same for you and me and everybody else, regardless of what they're doing, how fast they're moving, where they might be. None of that would affect the Newtonian, the classical notion of time. But what Einstein taught us is that when you think deeply about the force of gravity, you realize that gravity is tightly connected to the curvature of space. In fact, more precisely and more relevant to your question, gravity is associated to the curvature of space and time. Now, curved space is something that we at least can picture. You've seen those images. I use them all the time, where you've got the sun and space kind of warps around it. So you have some intuition about what physicists mean when they talk about warps in space, curves in space. What do physicists mean? What does Einstein in particular mean when he talks about curvature of time, warping time? What that means is clocks located at different positions in a gravitational field will tick off time at different rates. This emerges from Einstein's equations of the general theory of relativity. Nobody expected this. Nobody thought that this would be true. Nobody would have even considered this idea until it popped out of the equations. In fact, one way of interpreting what Einstein found is this. When you drop an object, we all know it falls downward, it falls toward the earth. According to Einstein's math, what's really going on here, the object is trying to move in a direction in which time elapses more slowly. Time does elapse more slowly on the earth compared to a clock that's ever higher up, ever further from the source of gravity. It's as if gravity pulls on time, slowing its passage. And this is such a crazy idea that nobody really would believe it until it was experimentally verified. And it was verified. I don't remember the exact year, but I believe the first experiment took place at Harvard. There's a shaft, as I understand it. I went to Harvard, but I probably should have looked at the shaft. I probably didn't know about this experiment at the time. But there's a shaft, I think, in one of the physics buildings at Harvard. And scientists use that shaft to shine light up and down the shaft. And light can be thought of as a clock because light is a wave that oscillates. And the oscillation of the light is like a tick tock, tick tock, tick tock, tick tock. So they were able to measure the tick tocks of light, the frequency of the light, as it went up and down the shaft, as it went further from the center of the earth, closer to the center of the earth, further from the center of the earth. And they found that indeed the clock slowed down the closer it was to the surface of the earth, and it sped up, relatively speaking, the farther it was from the center of the earth. So this is how time works. And I hope that gives you some insight as to where the idea comes from. But yeah, to have this in your intuition, pretty tough, absolutely pretty tough. Okay, other questions that I'll take from the live feed if I can find one. Why do some, Mr. Castle DK asks, why do some amounts of energy manifest as particles while others do not? And that's a good question. And it's a question that we can answer with a body of physical understanding called quantum field theory. Quantum field theory is the blending of quantum mechanics with the fields that we believe permeate the universe, the electromagnetic field, the gravitational field, the nuclear fields, the particle fields, and so forth. And within the equations of quantum field theory, you see that energy can manifest itself as excitations of these various fields. And when the energy is deposited in, say, the smallest possible excitation of a field, that is what we mean by a particle. An electron is the smallest possible excitation of the electron field. The photon is the smallest possible excitation of the electromagnetic field. Now, when you have a huge number of these excitations, say a huge number of photons, in some sense, they can fill out a wave. And now the wave-like description of energy comes to the fore. But when you're talking about excitations that are discrete, as opposed to a huge number of excitations all blended together into an oscillating wave, when you have a discrete, say, singular excitation, that's what we mean by a particle. And the ebb and flow of energy between these various ways that fields can be excited is determined by the mathematics of quantum field theory. So in the end, that mathematical equation or set of equations is the ultimate answer to your question, but intuitively, energy can ebb and flow between these various kinds of excitations. All right. Professor Greene, Corey O'Connell asks, can you explain how the mathematics within string theory combines both relativity and quantum mechanics? And yeah, sort of. So that's a big question. That's a question that would take, many episodes of the more pedagogical versions of your daily equations that we do every day or almost every day. Some of you may have noticed that I missed one day yesterday. It was the first day I missed in 17 days, so I hope that's okay. It became a little bit difficult due to various issues to get that episode out, but we'll pick it up with those on Monday. But to the question of how string theory puts gravity and quantum mechanics together, general relativity and quantum mechanics together, let me give you a quick explanation. So why is there a problem to put gravity and quantum mechanics together? There's a problem because quantum mechanics describes the world in terms of the quantum mechanical uncertainty principle, which will be next Monday's your daily equation. So you may know the ideas already, but roughly speaking, the uncertainty principle says the universe is always jittery, fluctuating, uncertain. And that uncertainty manifests itself larger and larger on smaller and smaller scales. And when you apply that uncertainty to the fabric of space itself, it means that Einstein's vision of space as a gently curving geometrical object, that picture doesn't work when you go into the microscopic realm because space itself is undulating so ferociously that it rips apart, it comes back together, pieces tear off. And those quantum processes applied to the fabric of space prevent the math of quantum mechanics and general relativity from blending together harmoniously. What does string theory do? String theory says, look, if your fundamental entity in the world is not a dot of no size, but rather a loop, a string of a particular small but finite size, then you can never probe smaller than that finite size. And indeed, when you look at that in detail, you find that the problem in putting gravity and quantum mechanics together only really emerged on scales smaller than a string. But string theory basically says there are no such scales. You can't probe any smaller than the smallest ingredient in the theory. And roughly speaking, that's how string theory triumphs. Puts gravity and quantum mechanics together by placing a cutoff on the small distance scales in the universe, thereby cutting out the potential incompatibility of quantum mechanics and general relativity. That's the basic idea. All right, what do we have here? Vivek Todaria asks, sir, and I like that. Thank you for calling me sir. It's so polite. I appreciate that. Let's see if I can get my kids to call me sir. I like that. Sir, can we know the center of the universe? There must be a place where the Big Bang occurred. And Vivek, I totally understand where you're coming from. If you think about the Big Bang as an explosion, an event in a pre-existing world, a pre-existing universe, then your intuition would be spot on. That explosion would have happened someplace in space, and it'd be interesting to figure out where that location was. But the modern view of cosmology suggests strongly that that's not the right way of thinking about what the Big Bang actually was. The Big Bang was not an explosion in a pre-existing spatial expanse that was already there. The Big Bang is the process by which space and time themselves came into existence. So the Big Bang, therefore, can really be thought of as taking place where you are now sitting, where I am now sitting, where that tree to my right is, where this coffee cup is sitting, because all these distinct locations throughout all of space, they were the same location in the early moments of the universe, because space itself in the form that we witnessed did not exist. Only through the expansion of the Big Bang did we get space that we are familiar with. So, in answer to your question of where the Big Bang occurred, I would say everywhere, because everywhere that we have access to was the same location at the moment of the Big Bang. Lala Zumba asks, hi, Professor Greene, can a black hole emit particles other than photons via Hawking radiation? And the question, and you're absolutely right. 1974, Stephen Hawking shocked the world of physics by establishing that black holes that we had long thought to be entities that only draw material in, they're black after all, nothing comes out of a black hole. Hawking showed that when you take quantum mechanics into account, that is not correct. Quantum mechanics allows a certain amount of radiation to leak through the surface of a black hole. And often when we talk about that radiation, we do frame it in terms of photons. And Lala is asking, well, okay, if photons can get out, can other kinds of particles get out too? And the answer is absolutely yes. The only special thing about photons is because they've got zero rest mass, it's somewhat easier, if you will, for them to emerge from the quantum processes taking place at the edge of a black hole. To yield heavier particles, you need more energetic processes, and those more energetic processes are rarer. But in principle, any kind of particle can be produced so long as its mass is less than the mass of the black hole. You still can't violate energy conservation, but so long as the particle has a mass that's less than that of the black hole, in principle, it can yield radiation of that particle through these quantum processes. All right, continuing onward. Let's see. Oh gosh, I got to keep this from scrolling so fast. I had a good one and then it slipped away. Okay, Scott Wilson asks, how can something with zero mass move? Because no mass equals no energy. And what Scott has in mind there, I presume, is that Einstein's E equals mc squared tells us that energy and mass are related in that simple mathematical formalism, which means that if n is zero, then E equals 0 times c squared. So E should be 0. So how in the world can a particle move if it has zero mass? It has therefore zero energy. And the answer to that question is, well, I should note that the answer to that question is covered in your daily equation. I don't mean that as an admonition. I mean that if you want to look further into the ideas that I'm talking about, go back to not episode 1 of your daily equation where I did E equals mc squared, but there's a later episode, and I wish I could remember which one it was, but in one of those later episodes I did address this question. But here's the answer to your question. E equals mc squared is actually a shorthand. It's a shorthand in 2 ways. Number one, as written, it only applies to particles that have non-zero rest mass. Moreover, the real way to write that equation is E equals m0 c squared times 1 over the square root of 1 minus v squared over c squared. There's a factor of gamma that comes into the real form of E equals mc squared, where you see energy in the sense of the rest mass of a particle plus the kinetic energy of motion. The velocity comes into the story there. But all of that derivation is really only true for a particle that has non-zero rest mass. For a particle with zero rest mass, we have a different formula. It's a formula that emerged initially from the work of Max Planck and Einstein himself in 1905 with the photoelectric effect, which is episode 8 of your daily equation. Well, I've covered a lot of these key ideas. And in that formula, we have not E equals mc squared, but E equals h nu. H is Planck's constant, and nu is the frequency of vibration, which when you apply that to a photon that has 0 rest mass, the photon is a particle of light. There is frequency associated with that light, and therefore the energy can be thought of as being embodied in the frequency, in the color, as opposed to the mass. And that's why a photon can have energy and why it can move, even though its rest mass to 0. You cannot apply E equals mc squared in the case of 0 rest mass. Okay, Dr. Greene, that was a good one. John Provatidis says, Dr. Greene, what are your favorite subjects to teach undergraduates? And John, if you asked me that question a few years ago, I would have said, I love teaching quantum mechanics. I love teaching general relativity. I love teaching a course that I made up called Geometry and Physics, where I put the mathematical methods of geometry together with physics and teach all sorts of cool stuff there. And that's what I did for 30 years. And I still teach those subjects. But I have to say that my favorite thing to teach now, and I don't mean this as an advertisement, I just did a live session in the hour before this with Reddit, in which I was talking about this thing over here. This is my book, Until the End of Time. And I teach a course based upon this book. And I have to tell you, that has been the most gratifying teaching experience of my life. And the reason I say that is, when you teach a course in quantum mechanics, and when we talk about quantum mechanics here, it can blow your mind a little bit. It's strange. It's weird. It gives you insight into the nature of reality. And I love that. And many students love that. And I hope that you all love that. But when I teach this book, which is trying to see where we human beings fit within these ideas and how we can find meaning and purpose in a world governed by quantum mechanics and general relativity, mathematical laws that seem not to care about us one whit. Teaching a course of that sort, you can reach students in a different way. I teach them about quantum mechanics and general relativity in the course, but I also teach them to try to grasp how the human species fits within the cosmological unfolding from the Big Bang until the end of time. And it's a much more emotional, it's a much more visceral experience than teaching quantum mechanics and general relativity. And that's why I have found it so gratifying over the last couple of years. So if any of you are going to be enrolled in Columbia in the fall, Columbia University is where I teach. I'm teaching this course. It is filled up already. But if any of you want to get into that course, and excuse me, I now have a tea leaf in my mouth. That's a little gross. Sorry about that. You should check it out because it's a course that allows you to think about scientific ideas in a different way. All right, let me scroll down here and see what else we got here. What does oh God, stop scrolling on me. I'm trying to hold this and it keeps going by too fast. I don't know why I can't hold it in place. Hello, sir. Another sir. I love that. How far are we successful in understanding dark energy? Asit Dash asks, and I would say we're very successful in understanding the implications of dark energy for the expansion of the universe. So we understand that dark energy yields a repulsive gravitational push, and it can explain the accelerated expansion of space that was discovered in the end of the 1990s. So that's great. But if you ask me, do I really know what dark energy fundamentally is and what its fundamental properties actually are? Are we confident that it has the equation of state that we use to explain the accelerated expansion of space? I don't. So there's a lot of observational astronomy that needs to be undertaken now and in the near future, which I hope will get us to that deep understanding that we as yet do not have. Okay, so Mike R asks, who creates our builder? And I guess what Mike means by builder is the creator, right? The creator of the universe that some people imagine is out there. And I kind of had this discussion an hour ago on Reddit, so I won't go into great detail. But I'd simply say, Mike, your question is the key one. Because if you imagine that there was a creator that created this universe, and that is the answer to why there's a universe at all, you're still left with the question, who created the creator, which is a question in my mind that's on par with why is there something rather than nothing? The deep question of physics, you're just substituting one word creator for the previous word universe, if you will. So I don't think a creator gets you very far, at least in a satisfying way, to the deep answers for exactly the question that Mike R asks. Who built the builder? Who created the creator? So here we have a question from no one. That's a nice name. Professor, could you record your lectures from Columbia University and release it on YouTube? That's an interesting idea. I have done that for some of my lectures. I didn't really do it on YouTube, but we have this website. You know, this is an event from the World Science Festival, which is an organization that I co-founded with the producer Tracy Day some years ago. And within the World Science Festival, we have something called World Science U. So it's going to be relaunched in about a week or two. So if you're interested, you can find a whole course that I did on the special theory of relativity. It's got hundreds of animations that were created by our wonderful team, including one individual who is producing this program right now. Josh Zimmerman created these wonderful graphics that are in the special theory of relativity course. So you should go check that out. I don't think it's available right now, but I think maybe April 29th is the relaunch of World Science U. So keep your eyes open. And there are 2 courses there from Columbia that I teach at Columbia that you can take for free online at World Science U. So Bhavya Shah asks, how far can we go into the multiverse theory? And look, here's my view on the possibility of a multiverse. It is an idea that naturally emerges from the equations of cosmology. There is a theory called inflationary cosmology developed by some of the greats of our age, Alan Guth, Andre Linde, Paul Steinhardt, Andreas Albrecht. Many people have developed these ideas in the decades since it was first proposed back in the 1980s. And in that theory, it turns out that it's very natural for our Big Bang to not be the only Big Bang. It's very natural in the mathematics for our Big Bang to be one of a collection of Big Bangs, maybe an infinite collection of Big Bangs, which would yield an infinite number of universes, and that would constitute one version of the multiverse. Do I believe this idea? Look, it's a natural consequence of equations that are really good at describing things that we do observe in the world, like the cosmic microwave background radiation. So these ideas are worthy of our attention. But I think it would be too strong for me to say that I believe in the multiverse. I believe it's an idea worthy of attention, but I only believe things that have observational or experimental support. And as yet, the multiverse doesn't have that support. So I allow it as a possibility, but I would say it's too strong to describe it as a belief or confidence in the idea of a multiverse. Okay, so I'm now scrolling through, and Rob Vandenberg. Rob Vandenberg. We used to have a neighbor here called Jim Vandenberg. I wonder if they are related. If I would move towards a clock at or near the speed of light, I would see the clock running faster because of the Doppler effect. And Rob, you're absolutely correct. When you talk about reality from the standpoint of physics, and in particular the special theory of relativity, you need to distinguish between 2 things. You need to distinguish between your perception of reality, the things that you would see, versus the objective qualities of the world responsible for creating the conditions that yield the light that allows you to see what's happening in the world. And it is the case that when you say run toward a clock, that clock's in motion from your perspective, which means according to the special theory of relativity, that clock is ticking slow from your perspective. That's the objective reality. But the light that clock is giving off, as you note, because you're getting closer and closer to the clock, the light has to travel less and less distance to reach your eyeball. And when you take that into account, your perception, your observation would actually be that the clock is ticking faster. But if you then unwind your observation to figure out what's happening to the clock for it to appear to be doing what it's doing, you realize that the clock has to be ticking off slower in order that the rate of speed up that you see matches your observation, matches the equation. So yes, you see the clock as though it's ticking faster, but the reality behind the scenes, so to speak, is that it's ticking slower. Important distinction. And if you'd like, in that special relativity course that I mentioned at World Science U, it may be available now, but certainly by April 29th, it will be available. There's a whole module on distinguishing between what I call observation and measurement. Observation is your question, what you see in the world. Measurement is what you deduce about the world based on your observations. And those need not be the same. I mean, anybody who's gone to a baseball game, right? You know that if you got the cheap seats, you're in the outfield, bleachers, when Aaron Judge hits that baseball, you see the ball fly off the bat before you hear it. That observation might lead you to think that the ball leaving the bat and the sound created by the bat are two different events because you see them, you hear them at two different moments. But of course, you know that your observation is misleading. You need to unwind it to figure out the actual reality of what created the stimulus that you're seeing and you're hearing. And of course, when you unwind it, you realize that the bat hit the ball and simply that the sound waves take longer time to reach your ears. And that's why your observations suggest that these two events are different when the reality behind the scenes is that they are the same. You have to distinguish between observation and measurement. All right. Farid Sedano asks, what are some of the dimensions predicted by string theory? Well, string theory requires that there are more dimensions of space than the three dimensions that we know about, right? You look around the world, what do you see? Like you look at an object, right? My book, right? What does it have? It's got length, it's got width, and it's also got height, right? Three dimensions of everyday experience. And that's the case of everyday objects. But string theory suggests that in addition to length, width, and height, in addition to left, right, back, forth, and up, down, there are more dimensions of space. And in a way, those dimensions are not particularly exotic. They're just like these dimensions of space. They're just much smaller, we believe, curled up into tiny shapes, so small that we do not see them. But other than that, space is kind of space. It's just more of them than we thought based on everyday experience. All right, what do we have here? Professor, what according to you is the future of science? What can we expect to see in our lifetime? Asks Abi. I'm so sorry. Abhichith Nag. I'm sorry. I'm so bad at being able to pronounce names that are unfamiliar to me. But that's a very good question. What can we expect to see in our lifetime? Let me say my dream. My dream is that we will gain insight into the true nature of space and time. We know a lot about space from Einstein, warps and curves, right? It can ripple, gravitational waves. Very recently, that idea has been confirmed through observation. We know a lot about time. We know how it ticks off. We know how it ticks off at different rates depending upon motion and gravity, some of which we discussed here today. But if you ask me what space is and what time is, nobody can really give the answer to that yet. Are space and time built up of smaller ingredients, like molecules and atoms of space and time? There's a suggestion in string theory that that idea might be true. And I would hope that in our lifetime, to answer the question, that maybe we will get to a point where we're able to answer that question. That to me would be the big dream. The other big dream, to just go to a different subject, is if we could gain an understanding of what consciousness is. I don't mean like sort of woo-woo consciousness. I'm talking about the fact that you and I both have these inner worlds of conscious experience. Where does that come from? How can it be that particles come together to yield the inner world of human reflection? That is an idea that I spent a lot of time in this book investigating, but there are insights into it, but the jury is still out. That would be another big insight that I would imagine or hope that we could one day get to. Okay, what do we have here? Let's see. So Kush, I was just about to do Kush's question. It went by. Come on, stop moving on me. Ernest asks, does space-time have mass? Because it can curve, so I believe it should have mass. And that is a subtle question. And the answer is sort of yes, right? So what I mean by that is, in Einstein's equations, any energy, regardless of the source, will have an impact on the curvature of space-time. And gravity itself, which is the curvature of space-time, can have energy, right? I mean, gravitational waves are ripples through the fabric of space-time. They have energy. They can make a detector stretch and shrink. That's how we observe them. And therefore, gravity itself can contribute to gravity. Gravity itself can contribute. The energy in the gravitational field can contribute to the warping of space-time. So in that sense, the answer is absolutely yes. Okay. Shital Angra asks, Professor, if the Big Bang created equal amounts of matter and antimatter, why don't we see antimatter around in the universe today? In fact, you could even ask that question a slightly different way, Shital, which is, if there was an equal amount of matter and antimatter in the early universe, by now wouldn't have the matter found the antimatter and annihilated into energy, so there'd be no matter or antimatter left? That is a puzzle. We believe the answer to that puzzle is that ultimately, in the unfolding of the cosmos, an imbalance between matter and antimatter emerged. And we have an understanding of the conditions necessary for that imbalance to take place. It requires that certain symmetries, called charge conjugation symmetry and parity symmetry, need to be violated. And we believe, we understand in principle, ways in which those symmetries could have been violated. And with that, together with the expanding universe, you can arrive at a situation in which there could be slightly more matter than antimatter. Slightly more matter than antimatter, which means, imagine that you have 1,000,000,001 particles of matter for every billion particles of antimatter. Then the billion particles of matter and billion particles of antimatter, they will annihilate into energy, and one particle of matter will be left over. And imagine that happening over and over again throughout the universe. You get a little residual matter left over, and that little residual matter may in fact be why we are here. If you're interested to explore that idea further, I should mention the World Science Festival, you're all watching this World Science Festival feed, has a program that we released a couple months ago. It's called The Matter of Antimatter. And it's a program that I moderated. I led a conversation among some of the world experts on the very question of matter versus antimatter. And it was kind of a fun journey through these ideas. So I suggest you check out that program. It's probably somewhere on the very page where you're looking right now, The Matter of Antimatter. Definitely worth 90 minutes to check that out. Quail Zachary asks, does light experience time? I'm sorry, or no, I'm sorry. God, my eyes are so bad. So it's not Quail. I'm going to try to get this one right. OU, whale, something like that. Anyway, I love the question, does light experience time? Because if you look at the time dilation of Albert Einstein, which was the second episode in your daily equation, so you should go check it out if you haven't looked at that, there's a factor called gamma, which is 1 over the square root of 1 minus v squared over c squared. I wonder if I can even bring that up on the screen here. And I'm going to risk doing that. Does this work? I'm going to see. Let's just see this. Love to use technology stuff. So if I can bring this up, I will try. Do you see that little scribble there? I think you do. Good. So what we did in that episode, we found that there's this guy called gamma, which is 1 over the square root of 1 minus v squared over c squared. And this factor, which was the daily equation for episode number 2, tells you the factor by which clocks slow down, right? And v is the speed of that clock. So if you notice, if you let v approach the speed of light, c, then gamma goes to 1 over the square root of something that gets very, very close to 0. And anything divided by 0, this is going to infinity, which means that a clock that's traveling at the speed of light would appear to slow down by a factor of infinity. which would seem to suggest that a light beam experiences no time at all. And that's the origin of the question, I presume. Does light experience time if you have this infinite factor of slowdown? And so roughly speaking, I can say no, photon doesn't experience any time. But you have to take that with a grain of salt, because like a photon's not a conscious being, right? And when you're talking about the experience of elapsed time, you have in mind your experience, and you're imagining that the photon's version is your experience slowed down by a factor of infinity. But the photon doesn't have conscious awareness, it doesn't have experiences. So the notion of time not elapsing for the photon is true poetically. It's true in the limit of mathematical equations, but I wouldn't take it too far. I like to think about it as the experience of all time at once. That's kind of pressing the issue into a place that I'd have difficulty condoning. So poetically, yes, metaphorically, yes, but literally, you have to be very careful ascribing the experience of time to a photon. All right. Then Sunny asks, can we go and come back from a black hole without any hindrance? And yeah, in principle, if you stay outside the event horizon of a black hole, right? If the black hole has a mass m, then there's a beautiful little formula that you can work out for how big the black hole is. You take 2, multiply it by Newton's constant g, multiply it by the mass of the black hole, and divide through by c squared. And that number tells you how close you can safely get to a black hole without being pulled in. And if you stay outside that number, 2gm over c squared, then in principle, you can go to the black hole's edge, turn around and come back. And if you do that, when you come back, you will note that you come back to the future. If you spend time near the edge of a black hole, time elapses there more slowly. So clocks back on Earth will be ticking fast while your clock is ticking off time slow. So if you spend like a year hanging out near the edge of a black hole and then you come back to Earth, it might be 10 years in the future, or 1,000 years in the future, or 1,000,000,000 years into the future. So the journey that you're talking about may seem to be a journey through space. You go from Earth to the black hole and then you come back, but it's actually also a journey through time, because when you go to the black hole and you come back, it will not be the amount of time that you think should have elapsed. It'll be much more on planet Earth. Okay, so how are we doing on time here? We got about 10, 15 minutes to go. So, where should we take from? Maybe I should go back to the YouTube and just grab one there just to keep this evenly divided. So Kat from YouTube says, hello, I'm Caitlin from North Carolina. Because the growth of the universe is accelerating, will the expansion ever catch up to the speed of light? And the answer, Caitlin, is yes. In fact, even right now, if you think about objects that are sufficiently far away, their speed is proportional to their distance from us, because the fabric of space is stretching, which means that the more fabric there is between you and me, the faster we will recede from each other. Galaxy is really far away from us, then it can rush away from us at a speed that's greater than the speed of light. And that means that we won't be able to see that galaxy, because once something's moving away from us faster than the speed of light, the light it emits will fight a losing battle to reach us. And the accelerated nature ensures that in the far future, all of the distant galaxies, the ones that are not bound to us gravitationally, the so-called local group, but all other galaxies besides the local group, they ultimately will be moving away from us at a speed that's greater than the speed of light. So when we look out into the universe in the far future, it's going to be dark, Caitlin. We won't see anything, because all those distant galaxies will have rushed away at a speed faster than the speed of light. We won't be able to see them at all. All right, let's see here. I'm asked by Prakash whether the fabric of space can tear. And That's a question that's kind of near and dear to my heart because in the Einstein theory, in general theory of relativity, space can't tear. In Einstein's theory, space can stretch, it can deform, it can warp, it can curve, and so on, but it can't rip apart. If space were to rip apart in Einstein's theory, the math, it just kind of falls apart. The thing just crashes and burns. And a project that we started to work on back in the 1990s, goodness gracious, almost 30 years ago now, a project that I worked on with a number of colleagues, we asked ourselves the following question, basically your question, Prakash. We said, look, if we look at how the space evolves, not in the general theory of relativity, which ignores quantum mechanics, but if we include quantum mechanics in the manner that string theory puts quantum mechanics and Einstein's theory together into a unified mathematical structure, could space tear in that setting? And we found that space can tear. We found a number of ways that the fabric of space could rip apart. And we found that when it rips apart, the theory is perfectly well behaved. The math does not blow up in your face. The theory does not crash and burn. So that doesn't prove that space actually tears in the real world, as we don't know if string theory is a description of the real world. But at least in the only theory that we have that can really address this question by putting gravity and quantum mechanics together, we find that space can tear, at least the mathematics says that ripping apart of space is something completely consistent with the underlying physical laws. So thank you for that question. Okay. Alice asks, hi, Brian, what is your favorite book? Do you have any book recommendations for people hoping to study physics in university? Well, it's hard to answer that question without sounding self-serving, but, I really do like my latest book. I really encourage you, don't have to buy it. Find a fake PDF online. They exist. Go to the library. I'm not trying to make money on this, but I think you'll find the story that I tell in this book, which weaves together physics as well as the concerns of a conscious, self-reflecting species called human beings. I think you'll find that journey interesting and gratifying. So that's one book that I would suggest. But in terms of other hardcore physics books, I would say that one of my favorites is Steven Weinberg's Gravitation and Cosmology, Principles and Applications of the General Theory of Relativity. I bought that book when I was an undergraduate. I had no idea what it was saying. It was well beyond my ability to understand when I was a freshman in college. But it's one of the best written books that explores Einstein's ideas by a true master of the subject. So from the science perspective, that certainly is a book that is worth having on your bookshelf, worth taking down from the bookshelf and actually reading. It is a masterful explication of the general theory of relativity. Okay, what else do we have here? Do we have time? Yeah, we got about 10 minutes or so. Let me find a good question that just fires me up. Okay. Vidish asks, what is the quantum measurement problem? Yeah, and I've spoken about it before, but it's such a vital problem. It's worth spending another moment on it. According to quantum mechanics, and this is again something that we covered in an earlier episode of Your Daily Equation. I don't remember which episode it was, but in one of the earlier episodes, maybe it's Schrodinger's equation episode, it could be. I discussed where the motivation for the quantum laws come from. And in there, I described how the new paradigm of quantum mechanics is to predict probabilities of outcomes instead of definite outcomes. That's the Newtonian picture is, tell me how things are today and I'll predict how they will be tomorrow. The quantum paradigm, the new paradigm is, tell me how things are today and I'll predict the probability of getting one or another outcome in the future. Now, the quantum measurement problem, your question is this. When you measure a physical system, you find one definite outcome. You never perform a measurement and say, well, I found it here and there. I found the electron was both here and there. That never happens. You find the electron here or you find the electron there. Quantum measurement question is, how does the universe progress from this probabilistic description in which the particle might be here, here, there, or someplace else. How do we progress from that to the single definite outcome that each and every measurement reveals? How does that happen mathematically and physically? And we don't know the answer to that. And that's the quantum measurement problem, and one that doesn't receive as much attention as it deserves because it doesn't affect our ability to make predictions. The probabilistic predictions are still there, but how to get the math to yield a definite outcome, nobody really knows. Okay, what else do we have here? Does gravity affect antimatter in the same way as matter? Crack, nice name. Crack asks this question. And the answer is yes. So matter and antimatter are particle of matter and its antimatter cousin, say the electron and the positron. One of the deep theorems of physics is called the CPT theorem. And that basically ensures that a particle of matter and the corresponding particle of antimatter have the same mass. And mass is the thing that gravity responds to. Mass and energy are the things that gravity responds to, as well as momentum in the general theory of relativity. So since the particle and the antiparticle, from the standpoint of their fundamental rest mass, have the same features, then gravity treats them in the same manner. Nexa's motion asks, can you please share how exactly the universe is finely tuned for life? And yeah, when we look out at the world and carefully measure it and examine it, we find that there are certain fundamental numbers that seem to be inherent to reality. Numbers like the mass of the electron, the mass of the quarks, the strength of gravity, the strength of the electromagnetic force, the strength of the nuclear forces, on and on and on. A list of about 24 numbers that we have measured with great precision. Nobody has any understanding of why those numbers have the particular values that they do. Nobody knows why the electron has its particular mass, for example. Now, you might wonder if we should care about explaining the values of those numbers. Maybe we should just accept them as a quality of the world. That's it. Now, the reason why we puzzle over an explanation for those numbers is because we have found that if we adjust some of those numbers, many of those numbers, by even a few percent, the universe as we know it would go away. Stars are the ubiquitous feature of the cosmos. Stars that give rise to the heat and light that bathes a planet like the Earth and allows life to exist. Stars would not light up if you were to change the electron's mass or its charge or the strength of the electromagnetic force. You fiddle with those numbers. Stars don't light up. Without stars, there isn't any life. So that's the sense in which the universe seems to be finely tuned for life. Those new numbers, those numerical values seem to have been set to just the right values to allow stars to shine, planets to form, and at least one such planet, life, to exist. Now, that's an interesting puzzle. One solution could be that we maybe live in this idea that we discussed earlier. Maybe you live in a multiverse. Maybe there are many, 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 many universes, and the values of those numbers vary wildly across all of the universes, and we simply live in that universe where the values just happen to be the ones that we measure, allowing for the processes that allow life to exist. So maybe we exist here and not another universe for the same reason why we are on planet Earth and not living our lives out on Neptune. This planet is hospitable for life when Neptune doesn't seem so. Maybe, similarly, we live in this universe and not another because this one happens to be hospitable for our form of life. That could be the answer. Or maybe there's a deeper explanation embedded within the mathematical laws of physics that we have yet to figure out. All right, so a couple more questions before we wrap this up. Okay. Again, a sort of similar question from Rethik to the time question that happened earlier. Since there's infinite length contraction, does space or the universe exist for a photon? So that gamma factor that I brought up earlier that gave us that infinite time dilation, gamma equals 1 over the square root of 1 minus v squared over c squared, v approaches c, gamma goes to infinity. that infinite factor also suggests that the universe would crush down in its length to zero size from the perspective of a photon. And my answer is basically the same. Poetically, sure. It's as if the photon experiences all of, say, space along the direction of its motion simultaneously, because it's all one location. It's all squeezed down. But it's only poetically, it's only metaphorically. Taking the perspective of a photon is a perspective that you and I and no sentient being will ever have. We will never travel at the speed of light. We are massive objects. We are constrained to travel at a speed less than the speed of light. So taking the perspective of a photon is a poetic perspective, but it's not a perspective that any of us will ever have. And that's what I mean by you have to take it with a grain of salt. Okay, what else? What else? Let me find maybe something over here. Emily asks, why must the speed of light be constant? And Emily, I don't know. There are theories, in fact, that investigate the possibility that the speed of light is not constant, that the speed of light may have changed over the course of cosmological history. I can imagine, moreover, a universe, not our universe apparently, but a different universe, a potential universe. Maybe it's not real, but I can imagine the logical possibility of a universe in which the speed of light is not constant. So the best answer that I think science can give to your question, Emily, is that the speed of light being constant is a weird idea. It is a counterintuitive idea, but it is an idea that allows us to explain observations and experiments. When you assume that the speed of light is constant, all of a sudden, many puzzles completely fall into place. And that gives us confidence that this weird idea is actually true. It doesn't necessarily mean that the idea is logically required to be true. You can imagine a reality perhaps where it's not true, but in this reality, apparently it is true. So we take it as a given and we go from there and we draw all sorts of conclusions based upon the constant nature of the speed of light. And each and every one of those conclusions is borne out by observations. And that allows our confidence in the constant nature of the speed of light to grow. And then we come to this conclusion that it is constant. But other than that, there's not much further, I think, at this point of understanding that we can go. All right, let me see if I can find one more to do here. So Sheila from Oklahoma asks a question. Sheila said that she was on the Reddit question and answer that I did just an hour before this, and she had a question there that didn't get answered, so she's asking it here, which is fine. She's asking a question. So if you were going to talk about the main idea in your new book that puts these ideas together, she lists a number of them, but if you put these ideas together from physics to human reflection, what would it be? And this is actually a question, Sheila. I don't know if you stayed around to the end of the Reddit. I sort of did discuss this a little bit at the end, but I'm happy to do it here in this different context. Look, I don't think that we're ever going to find purpose and meaning written into the fundamental laws of physics. I don't think that within the equations of general relativity or quantum mechanics or whatever the future laws of physics that we discover may be, I don't think you're ever going to find a place in which you're going to say, aha, there is the reason why we humans are here. There is the purpose of life. I just don't think that the universe is built that way. We are collections of particles governed by those physical laws, and it just so happens that for a brief period of time, the ingredients come together to yield conscious beings like ourselves, and conscious beings can begin to question reality and begin to wonder about where we came from and begin to wonder why we are here. And that's just a natural outgrowth of the evolving nature of complex particulate arrangements, at least some of those arrangements that take place on planet Earth. So my view is you don't look to physics in that sense for that kind of flat-footed, straightforward directive as to what meaning and purpose there is in the universe. Rather, you look to physics to understand the framework, the context within which living beings such as ourselves exist. And within that, as I describe in the book, this guy over here, within that, you can find a certain kind of gratification that we can understand the universe and that we can question the universe and that we can create great wonder and great beauty. I mean, look at what we've done as a species, right? We built the pyramids. Beethoven writes the Ninth Symphony. Shakespeare, Julius Caesar, Macbeth, Hamlet, Walt Whitman, Leaves of Grass. I mean, coming into the modern age, look at all the beauty and wonder that we can create even in lockdown. Have you been watching the kind of creative things that have been put out, even just on YouTube, where we have been able to show that even when we are challenged by this global pandemic, there still is the creative spirit that can reach out and create things that can touch us. And to me, that's the wonder of being alive. None of this takes away sort of the pain and tragedy of being part of a world in which there's death, destruction, pandemics that can make life so difficult and tragic and end it for some of us. But to see that in the context of the unfolding of the cosmos, and to see that in the context of these beautiful laws of physics, simple ideas that can yield the complex experience of human life, to me, even when we recognize that our existence is fleeting, the fact that we exist at all is cause for celebration. It's cause for a sense of reverence. And if that's the one message that I would say I sort of really try to talk about in this book, that's, Sheila, what it would really be. All right, anyway, that's about it for today. I think I've gone over my time a little bit by a couple minutes. Come back on Monday for the next episode of your Daily Equation. I will do Heisenberg's uncertainty principle. And then if you're up for it, next Friday, I'll do another one of these live sessions. Until then, though, this is Brian Greene for your Daily Equation World Science Festival. Also, subscribe. See that little button over there? You subscribe to the World Science Festival, all sorts of great content. If you want, you can follow me personally on Twitter, bgreen at Twitter, or on Facebook. In any event, though, I will see you at the next episode on Monday of your Daily Equation. Until then, take care.